Yeah.
Okay. So you can hear me well. Perfect. So yes, this is the time now for Team 3. So the science and instrument connection. So I will be sort of leading this talk, but then you will hear also from Philip and at the end from Roman, who will present his work on NFIT. So, oops. Yeah, so the outline of this report would be, okay, a brief introduction, particular for the newcomers, so they know who we are and what do we do. You will see we have working groups in Team 3, so we will have the reports of the working groups, then the final remarks, and then in the last 10 minutes, Roman will present the work on the NFITs. Okay, so who are we? So this is basically the crew that regularly participates in the Team 3 meetings. And yeah, everybody is of course welcome to join us in this. We are currently Jens, Adrian, and I leading this group, but I would say it's very horizontal. So this is just more for administrative issues rather than all the thing. What do we do as team leaders? So what do we do? So we have heard Tim and Eleonora presenting Team 2. Basically, they are driving the science, defining what the science requirements of the mission are, what is the target database, and all the science that we would do with life. And then we have the Team 4 that is basically focus on more the technological development, the mission concept, the knowledge technology. And we are sort of the team in between, the one that tries to connect the science we want to do with the technology available and how do we translate things from one place to the other. And for that, we are divided into 4 working groups. So the first one is about defining the mission requirements. The second one is about the simulators. You are very familiar with LiveSim, and there are other simulators. So here is where also a lot of action happens. Then the signal processing. So how do we interpret the signal that we get and how do we process it? And finally, the mission evaluation. How do we work? So we meet, or let's say we have met online 7 times since the last all hands meeting. Basically, we wanted to have a rhythm of 1 meeting per month, but we find it not to be very efficient in this way. So we will introduce a new format starting from the next meeting. So the idea now is to meet once every 3 months and put more emphasis in the work of the working groups and having these Team 3 meetings as a moment where there is a more formal report from the working groups and we have a high-level conversation to exchange what each working group is doing and how should we proceed. The next meeting, for those that would like to join, is on the 18th at 11. And if you want to receive our activities, what do we do, when do we meet, please join us in the mailing list. So we usually track everything that we do with a software called Redmine. For accessing it, you need an account. So if you're interested in participating in Team 3 and getting to know what we do, please write to me or to Jens. So this is the overview of Team 3. Now we are going to the specific reports of the working groups. So I will talk about the working group 3.1, the mission requirements, which I'm coordinating. So we started this year at full speed, meeting every week, every Friday at 11:30. We have had already 21 meetings, and of course, if you want to join, you can write to me. Being part of Team 3 and the working groups is not exclusive. You can be part of one of Team 3 and not of the working groups, and also the other way around. So don't feel that you need to have everything if you want to participate. So more specifically, what do we want to do with the mission requirements? So we take as an input what the science team wants, so the science requirements, what are the objectives of the mission, and we try to get the input for the concept study, so to have all the objectives and the high-level requirements of the missions, also put constraints, like reasonable constraints in terms of I don't know, extent of the lifetime of the mission. We cannot say that we are going to observe for 100 years. So these kinds of things that constrain things towards what is reasonable, but also with the objective of achieving the science requirements. And this is an iterative process, right? It will go back and forth between the two teams, right? That's why we are at the interface. So what is possible from the technological point of view and what the science needs to do for this mission to fulfill the objectives. And we try to write things in a way independent of implementation, so see really what we require from the mission to reach the science and not to put constraints on what is possible from the technical part. So we are not going to define what is the size of a telescope, but we are going to say how much time do we need to, or to put a constraint on how much time we are spending in observation of a planet to get the, for example, the signal to noise ratio that we want. And then these mission requirements will be an input for the system requirements and specifications. So we are now working with the two main science requirements. So the one that defines the search phase, search campaign, which reads something like life shall identify for subsequent characterization 30 to 50 habitable exoplanet candidates orbiting single mature main sequence stars. So these are the FGK stars, solar type, and this is referred as a search campaign. And then we have the second stage, that is the characterization of the atmospheres identified during the search campaign. And we have to start from the beginning. So first we have to find the planet. So that's why we are focusing on the search campaign, where it was, we noticed that not much has been done, and it's the most basic thing that we need to start moving with the mission. So basically, what we need to, or what our objective is, current focus is to define the requirements that will allow us to identify these habitable exoplanet candidates, which implies determining the planetary nature of a signal, and that means providing, after a certain number of observations, the radius and the effective temperature of the planet and its orbital parameters. All these things to be able to say, okay, this is a candidate that is worth characterizing or not. This involves the definition of which is the wavelength range we want to, for this to happen, what is the resolving power to determine the radius and the effective temperature with the desired precision. What is the precision we need in angular separation to determine the distance and therefore the albedo and the orbital parameters. Then we would like to develop a statistical metric to determine the likelihood of a planet being habitable, and what are the models that connect observables and measurements. Another thing is to define requirements to be able to complete the search campaign in a reasonable amount of time. What are the requirements to run a certain field of view that contains the habitable zone of the stars of interest, and define the requirements to maximize the sky coverage. So we are quite advanced in the sense of the ideas that we know what we want to do. Now is the time to implement what we want to do into simulations, and for that we are missing some manpower. So I call for people interested in helping us with simulations of these kinds of studies to join us, because we really need some hands on this. And with this, I ask Philip to continue. Oh, sorry.
Yes, hello everyone. So I will be speaking on behalf of the simulations and the signal processing team. So the reason for that is simply that we had a lot of close collaboration in the last couple of months, and also quite an overlap in the topics that we worry about. So yeah, we thought it makes sense to put these two slides together. And also you might have seen on Slack that we have started a new common meeting, but more about this in a few seconds. So I would also like to give you a quick summary of what we have been doing so far, or since, yeah, maybe since the last all hands meeting. So I'd say the main topic of our two working groups is the impact of instrumental noise and related aspects. So as you might know, in recent studies or previous studies, we have mostly not modeled instrumental noise explicitly, with some exceptions, for example, work from Jonah Hansen. But we have mostly assumed that we only have fundamental noise. So, for example, astrophysical noise. So what we have been doing in the last months or years is developing frameworks that allow us to now model the effects of instrumental noise. And the particular aspects that we are currently looking at is first the non-Gaussian nature of this new kind of noise. So this is mainly the work by Felix Dannert. Studies also in preparation. So what Felix is mainly doing is the following. So far we have assumed again the noise is Gaussian in our hypothesis testing. So it turns out it is not. So what Felix is doing is proposing a new test that can deal with this non-Gaussianity of the noise. Then another aspect we are looking at, this is mostly the work of myself and Romain and his students, is correlated errors, and then the data processing techniques that can deal with these errors. I've brought you a little teaser here of the study that is in preparation in this regard. So you can see here 4 panels, all showing the same planetary scene. So there's one planet in the upper right corner. The other bright spots are basically artifacts. So on the left side, you can see how this planet looks like, basically with the assumptions that we have made in previous studies. So no instrumental noise at all. Then if we move one panel to the right, this is how the scene looks like if we add the instrumental noise. So much more noise and artifacts in this reconstructed image. And then finally the 2 panels to the right is how it looks like if we then apply some clever processing techniques. Yes, so much about that. Then another topic we are currently dealing with is traits. So again, there have been a few traits in previous studies, but what we are doing now is revisiting these traits in the light of instrumental noise. So for example, trading dual Bracewell versus kernel nulling. This is currently mainly the work of Romain and one of his students, Lien, at TU Delft. Another topic that is related to all of this, of course, is covariance estimation and shrinkage. And this is the work also from a student, Louis, at KU Leuven. Now, in the context of all of this work, we are, of course, also developing new tools, not just for us, but also with the idea of them being useful to the community. As you can see, we have divided them into these 3 boxes. On the left one, we have, or in the left box, we have LiveSim. So this is the version that is described in Dannert 2022. So the one that probably most of you have been using if you have used LiveSim before. Yeah, and we labeled this box Science Performance. So as you may know, this LiveSim version does not include any instrumental noise. But if you are interested in pure science performance and basically don't really care about the amount of instrumental noise we can allow for in our instrument, then we would still encourage you to use this version of LiveSim as the main tool for your studies. For everyone that has not used this before, there's actually a tutorial on YouTube. So if you search for LiveSim tutorial, then you should find this video here. There's the thumbnail of the video that explains you how to use this tool. Then everything in green here shows the new tools that we are currently developing. Oops, there goes the presentation. Should I can quickly share myself. Second. Okay. So you should be seeing the presentation.
Yes, we are
Very
back.
good. Okay. Where was I? So we have the new tools. Then the second box is, so we labeled it requirements derivation. So these are basically two new versions of LiveSim, but they have a very specific purpose or use case behind them, which is the derivation of requirements. So both of them are still in development. One of them is called LiveSim MC. This is what I'm working on. This uses Monte Carlo sampling of instrumental noise. It is available on my GitHub if you're interested, but again, still in development. The other version is called InLiveSim. This is mainly what Felix has been working on, and it features an analytical noise model, but it's currently not publicly available. Then there are also two new tools in the box data handling. So one of them is Fringe. So this is what we use also in LiveSim MC for the generation of synthetic data. So if some of you is interested in just pure data rather than the full or semi-full end-to-end tools, then feel free to use this as well. It's also available on GitHub. And the other thing is the new NI-FITS Python package, which mainly Romain is developing in the context of this new data standard. But we're going to hear about this in a few minutes. So then, in conclusion, we really hope that we can foster a bit the collaborations between our team and teams 2 and 4 in the future, also in the context of these tools and in the context of the market of projects, as we have heard before by Eleonora. And so we would encourage you to join our meeting if you are interested, or just reach out to us if you think these tools are useful for you. The meeting again takes place every other Thursday from 9 a.m. to 10 a.m. with the next one taking place in 6 days, so next week on Thursday. And I think that's all from myself.
Yes, thank you, Philip. So
should I continue with the slides?
Yes, please. So here, so Jens unfortunately couldn't join today. He's traveling back to Europe from Chile. So it's about working group 3.4, sorry, the mission evaluation. So basically it deals with exoplanet shield estimates, the development of the imaging simulator. And if you have any questions, please write to Jens. So the thing with this working group, I think, is the lack of people other than Jens, more or less. So the group is somewhat dormant at the moment, but it is expected to ramp up again when shield estimates are required to translate the science into mission requirements. And regarding the development of a basic imaging simulator, this is something we have discussed on several occasions in Team 3. It is ongoing, but slowly, because it's not a priority for the people involved. So we would need, again, more involvement of people that are interested in the imaging simulator to sort of try to push this forward. Next slide. Next slide. Okay. So yes. So then so the more efficient work, so the final remarks. So we are reorganizing the team 3 to have a more efficient work organization. So the working groups will carry out now the work, and team 3 meetings are the forum for the high-level discussions and yeah, the way forward for the big picture, let's say, of team 3. The working groups 3.1, 3.2, and 3.3 are active and hold regular meetings. The 3.4 is dormant, but is ready to wake up as soon as we get more people involved. And yes, I repeat it again, we need more people, so need help with simulations, analysis, etc. So really investment of time to use the tools and to help us with the different ideas that we have. Yeah, and next slide. So again, if you want to join us, please contact me or Jens, and we're very happy to answer questions that you may have. And this is all from my side. So I guess, Roman, if you want, you can continue.
Yeah, I have a couple of slides, if I can share my screen real quick. So I'm gonna try to run through them because we don't have a lot of time. So the idea is to present to you a little bit about the NIFITS nulling interferometry data standard and what it can bring to life. So quick explanation here. This is not a work that is entirely just a life effort. It is also an effort shared by the Asgard Knot team for the new nulling interferometer for VLTI, and as well as other nullers such as LBTI and Glint on Skexo Subaru. Just starting with quick words to remind everyone that we are not just after the pretty picture or even just the pretty spectrum. What we are looking for are sort of numbers, parameters of the systems that we are examining. Parameters, for example, such as position angle, separation, diameter, atmospheric profile, composition, and etc., etc. As far as you want to go in terms of model. So basically, to remind you what we are doing mostly in astronomy, in general, is that you have your target, your instrument observing it, and you record some outputs that you will store in a file. And then on the other hand, for interpretation, you're gonna sort of imagine what this target was, trying to find the parameters, the different parameters of this model, as I was just saying, and you sort of have a sort of simulation of your observation process, which gives you sort of an output model, and you will compare this output model with the actual output that you had recorded, and try to improve this iteratively or analytically to obtain to go back to the parameters that you have. Now, when you're doing imaging, so normal resolution, what I would say, either with imagers or coronagraphs, this process can be really straightforward because of the optical geometry relationships between pixel position and position in the field of view. And so you can just go with maybe some form of yeah, just adding some of the instrument parameters, such as the convolution by the instrument function. When you're going to what we call high resolution with interferometers and long baseline interferometry in general, the problem is a little bit more complicated mostly because what the information that you're obtaining is really partial, right? It's really not the complete information. You are sampling it at what we call UV points that depends on the different baselines of your telescopes. And basically, the way we've been working is using the OI-fit standards, which basically directly directs you to the Zernike-Van-Sittert theorem, and basically having you store information directly related to each baseline and therefore each spatial frequencies, right? Since the visibility of fringes is the Fourier transform of the intensity distribution sampled at the UV points. And the thing to keep in mind is OI-fits was really meant to work under this assumption. Now, when we want to do nulling, we're not actually recording fringes for each of those baselines. What we are recording, for example, in the life from life paper 2, sorry, would be the combination of all of the four, I mean, on the two outputs that are most interesting to us, combination of all of the lights from all four telescopes together, and we are looking at the flux or the intensity in that. And therefore, it doesn't really make sense to try to stick with the Zernike-Van-Sittert theorem, and we're going to have to look at something else, especially since this configuration that I was just mentioning is just like one of the possible configuration that have been mentioned. There's a configuration with 5 telescopes, 4 telescopes, but 6 different outputs and stuff like that. And even full pupil, things like full pupil vortex fiber nuller, for example, this type of things. And so that's where we are trying to introduce this NI-fits standards to sort of allow anyone to make use of the data without the need for them to have expertise on the instrument simulation of the particular instrument that is being used. So the way we've been doing that is basically imagine that you have a magic recipe where you follow a series of steps, and depending on what ingredients you apply those steps to, you end up with just the perfect dish corresponding to those ingredients. Well, here it's basically the same thing, right? The NI-fit standards, which sits here, sort of instructs the creator of the file how to basically take in all of the parameters of the instrument and put it correctly into the file. And another person who have maybe created a library that applies the specific equations that are shown here for the example to those data. Basically the user doesn't have to know all of the details of the instrument, because all of that is stored in the standard way into the file, and they can just query the library, and the library, for example, for a given position, will be able to exploit all of the metadata to produce what was the transmission of the instrument for this given point. And here, as you can see, this is an example, for example, like in this case, of having the transmission maps here, the differential transmission map. This was for the Asgard knot system, and this was for the LBTI nuller, which is a completely different architecture, extremely almost opposite in ways of functioning. But through this logic, they can just be interpreted in the same way. Here is a similar example for like the fringe setup that is the new way to produce synthetic data. Basically, you have your complex amplitude transfer matrix of the instrument. You have the locations of the collectors for each frame, and then you can just query your map to have the interesting data, either as a field of view raster, as you can see, as you could see in the previous example, or for arbitrary points for a moving planet, for example. This adaptation of fringe to produce NI-fits has been powered by Luce. So now this was just an example of one file, but let's not go into that. So the question is, what now? What changes? So I think the use and the proliferation of this standard can be transformative for nulling interferometry in practice, in application for the observers, but maybe also for simulation and considering the tool and estimation of performance. So there's a poll open to the community to try to constitute a community of nulling data users. We're planning to do a hackathon to help people kickstart their own application using the standards. That will be early next year. Hopefully, this will help us to avoid creating throwaway code and have code that can be iterated upon and shared between projects. We are currently implementing support for NIFITs inside OI Modeler, which we will use for NOT, for example. It can be used also for life. Indeed, Luce is setting up Fringe to export to NIFITs. This should allow pretty much anyone to start interpreting nulling data. But what I want to emphasize is we hope that this will increase communication between Team 2 and Team 3 and not the opposite, right? So I hope we can use that as a better exchange framework. And finally, I think this is opening the door for something that we've been asked repeatedly, is a live data challenge, possibly even HWO plus live data challenge, hopefully for SPAE 2026, and maybe iterations of that or training runs before that. So we are really happy that we can finally bring that on the table. Thank you very much.